hi to her and Jack, you can. Maybe they heard you say happy hello, happy Halloween to them. Hopefully Annika feels better so she can go trick-or-treating later. So. Okay, I think I'm on the right page. Let's talk about complementary angles. Let's look at, this is similar to, or what we're going to be doing is page 12 of 12 there, part of it. And let's take one chart here. Let's take a look at, what do you guys know from your chapter blocks? If I was to launch something up at 30 degrees, okay, that would go up and then land, right? If I go at 60 degrees, it goes up and it also lands there. I ran out of space. Now, how do those relate to each other? Okay, this one's 60 degrees. Let's look at those. So say you had on here, it says it's launched at 40 meters per second. It angles at 10, 30, 45, 60, and 80. So let's look at the second chart. The first one would be 10 degrees, but the second chart down, this one, that would be your 30 degree one. So what do you do first? So we'll do 30 degrees. What do you have to find first? The x and the y components. So at 30 degrees, we have this vector. It's launched at 40 meters per second, and we want to find Vx and Vy. Our y velocity and our x velocity. Well, what's my formula for the x velocity? V cosine theta. V is 40 meters per second, cosine of 30 degrees. The second one down. The first one would be 10 degrees. Yes. 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 40 cos 30 is, I just heard it in my brain, 34.6 meters per second. And our initial y is V sine theta, right? So that would be 40 meters per second times the sine of 30 degrees. Anybody know offhand what the sine of 30 is? What? Well, this whole thing would be 20 meters per second. The sine of 30 is 0.5. Well, because it's a special triangle, 30, 60, 90 triangle, the sine of 30 is 1 over 2, or a half. Okay. And then the cosine of 30 is square root of 3 over 2, but you do more of that in math. Here, you could just put it into your calculator and find it, right? You know how to do that, right? So now it's important that we look at this and answer correctly. So it says, launch at these angles. Fill in the charts for each launch. For each situation, just do the vertical rise in the y row, but do the whole motion in the x. Okay? So we know that. We also know this. This is positive going up. Oh, this is always down. It causes it to slow down going up and speed up going down. Now, if we're only going up in the y, stop. Oh. What is our final velocity then? To find out how high it goes. We're going to have it at 0 because we're just going to do the up part. These stay the same. This plus this divided by 2 is this. This minus that is that. Shortening my words. Delta T is delta V over A, or minus 20 meters per second over minus 10 meters per second squared. So that gives you 2 seconds, right? So from that now we can calculate how high it goes. So you have to be careful because if you do the whole parabolic motion, what's our displacement change in the y? 0. But in this case, we want to know how high it goes, so we're only doing half of the motion. But that's going to be important because what's that going to tell us to do to the time here? We got to double it to 4 seconds because we want the whole motion. This is just half of it, right? But we want the whole thing in the x. We can get delta S from V bar times delta T, where V bar is 10 meters per second, and delta T is 2 seconds, so that's 20 meters. So how high do we go? 20 meters up. How far do we go? Well, we can calculate this from the same equation. Whoops. .6 meters per second times 4 seconds. .138.4 meters. Okay? Well, we're going to get to that. So for the x direction, for 30 degrees, we get in the x direction, it goes 138 meters. And how high it goes is 20 meters. Let's see how that changes for 60 degrees. Well, look at the diagram that's chopped off here for 60. What should be the same for the 60 from the diagram? The x should be the same. Should the y be the same? No, it should be different, right? And what about time? Should the time be the same? The time should be different. So, but let's see if that x is the same. So we'll look at 60 degrees. Now that would be how many charts down for you? Yeah, because we got 10, 30, 45, 60. So the second one from the bottom is 60 degrees. Well, you got a pencil, so you can fill it in. All right, so cosine of, 60 degrees, 40 meters per second, Vx and Vy. Vx is V cosine theta, which would be 40 cos 60. Oh, what's the cosine of 60 degrees? 0.5. So this again is 20 meters per second. Oops, sine theta. So 40 sine 60 So Mikhail was saying, I think, are they just switched? Is that what happened? Or you said that. Are they just switched? And yes, they are, right. So the Y one comes to the X one. Excuse me. The average is 17.3 minus 34.6 minus 10, 3.46 seconds. V bar to get the distance up in the Y. .8 round up, so about 60 meters up we go. Now what did we go up in the other one? Only 20 meters, right? Now these are 0. This would be 3.46 seconds. Okay, now I got Kelly telling me, how would you know it's the same delta T? And Courtney saying what? Oh, right. So I made a mistake because we want the full X, right? So if we look at our motion, it's this. Now we did only half the Y so we could find out how high it went, right? So that's our delta S in the Y, but that's only half the time. I need to get double this, which would be, what? 6.92 seconds, right? Because for the X, I want the whole motion, right? So good. This is 0. And then delta S is V bar times delta T, 20 meters per second times 6.92 seconds. Let's see. What do we need to be? What do we need to be? 138.4. Now, when you fire the man, well, or you might, or the grand piano, whatever you choose to fire in the projectiles of the internet activity, it won't land exactly on the spot because if you look, the cannon's being tilted up so it's not leaving at the same spot. Okay? You have to be a little careful with that. So we do see that. Now we're going to go back to page, wait, number 7 on page 2 of 12. Kelly kicks a soccer ball. It actually just says a soccer ball is kicked. Who's a soccer star? Do you play soccer? Soccer? Mikhail kicks the soccer ball. Initial speed of 15 meters per second at an angle of 25 degrees. How long is it in the air? How far away does it land? Okay, so we want how long is it in the air and how far. So in this case, we're not interested in how high it goes. That's not asked. Although when you kick your balls in gym, PE class, we'll go over there and shoot videos of them, then we might be interested in knowing how high it goes. And we'll try to fit curves to the data too. Calculate that initial speed. Maybe in the X and Y. Okay, so what do we do first? Well, I know this. What else do we got? Anything? Oh, that's a good idea. Let's find this Vx and this Vy. Okay? Well, Vx is V cos theta, 15 meters per second, cosine of 25 degrees. You know, I see students mix this up and put 25 and 15 in the wrong place all the time. So be careful. .6 meters per second. Now we know that stays the same. We can get our Vy. That's V sine theta. Right? Uh-oh. That's the theme of the day. I make mistakes. See if you can catch them. There'll be other days that I just make mistakes. Hopefully you catch them because I don't know I'm making them. 6.3 meters per second. Now, if I always like this because that goes in here, and if the Vy going up is 6.3 meters per second, then when you get down to this point right here, it has the same Vx. Whoops. I can't really draw it there because of the way I drew it, but what could I do? I could shrink the whole thing down. No, don't clone. Oh, I just moved the whole thing over. That's fine too. That worked. Sorry. It's better that's off anyways. All right, there's that. So once it gets over here, we'll have the same 15 meters per second, and it will be found with this Vx of 13.6, and the Vy at this point is what? Negative 6.3. So you see where that comes from? So this is actually minus 6.3 meters per second. Um, yes. No matter what angle, as long as you end at the same horizontal height. In the asymmetric ones, you'll do for 3, 3, those ones will be not the same. But that's all right. So, what was I going to do? Oh, okay. So what's the average velocity? Well, it's VI plus VF over 2, right? And VI is 6.3 plus or minus 6.3. So the average velocity is actually 0, right? How is that possible? Well, what's your displacement? It's also 0 in the y. Delta V, though, is not 0. Delta V is VUF minus V, or minus 6.3 meters per second, minus 6.3 meters per second, or minus 12.6 meters per second. Delta T is this over this, or 1.26 seconds. See how I got that? This divided by that is that. Delta T is delta V over A. Okay? Now, how do I get delta S? We'll get it for both of them, right? For Y, it's just 0 times, oh, it's just 0, isn't it? I heard someone say, 17.1. I've had classes where we've used these things in the past. They're always fun. These are fun little things to take to your house for Halloween, too, you see. You take this, and you push this down, and then as kids come to the doorway, you know, you fire at them. We'll bring some of these over and videotape them as well. I wanted to do it tomorrow, but I got those parents in, so we'll have to start shooting your lab thing. So these are a lot of fun. Okay. Warning, don't look at it when you're pulling this out. Okay? It hurts. I'm sure it has. You should have safety goggles on, although I never make you wear them. Oh, edit out of video. Proof if you get injured. All right, I just want to look at some motion as it travels, okay? As the projectile travels. So we could take a ball. We'll shrink it down a bit. Let's give the rest of the person on there. Okay. Now the ball, what is? Tom, we're always nice in this class. There's the kick. Now, let's say that it leaves at 30 meters per second. That's quite the kick, by the way, but 40 degrees. This is just me talking. So it has a component of, it has a horizontal component, Vx, and it has a y component, Vy, when it starts out, doesn't it? And we can find Vx from V cosine theta, and we can find Vy from V sine theta. And so if you do those calculations, you'll see 30 cos 40 is 23 approximately meters per second. And the y is 30 sine 40, or 19.3 meters per second. Okay? Now, how does the x component change through flight? How does the x component change through flight? Will? It stays constant, doesn't it? So with all of these, it has the same x. Okay? Now the y component, it does change. What would be the y velocity 1 second after it takes off? So if this is t equals 1 second, wait a minute, no, hold on, I got to do that right. Yeah, let's say this is a t equals 1 second one. Well, what does it start with? So how much will it reduce going up? By 10. So it started at 19.3, so 1 second later it's going to be going 9.3. So then right here, you got a Vy equal to 9.3 meters per second, but you still have the same Vx of 23 meters per second. So you might be interested in getting what the overall velocity is at that point. In that case, to get that overall velocity, you would do Pythagorean, right? And so V squared would be Vx squared plus Vy squared, which would be V is the square root of 23 meters per second squared plus 9.3 meters per second squared. Right? You see how I did that? Because if you have your x and y components, you can get your resultant. So square root of 23 squared plus 9.3 squared gives 24.8 meters per second. What angle would that be at? What's the theta here? Well, the theta would be the tan inverse of Vy over Vx. Remember? Use tan inverse to get the angle. So theta would be tan inverse of 9.3 over 23 or 22 degrees. See? Now once we get the t at the top, which would be 1.93 seconds, what's our y go to? It goes to 0. So Vx, it's all Vx, and our velocity at that point equals 23 meters per second. So you could get your Vx and Vy at any point on your path. Use Pythagorean theorem to find the magnitude of the overall, and use tan inverse to get the direction of it. Have a nice Halloween night.